This hit and run is on the Gauss-Markov Theorem. And I like to do a hit and run sometimes when you sort of wish in live class you could just pause, and stop and reflect on something. So I'm probably going to go faster than you can really take this in and understand it. We'll discuss it some in our live sessions. Uh, but hit that pause button frequently in what we're about to do if it helps you, certainly. The Gauss-Markov theorem says that with well-behaved data and errors, ordinary least squares estimates are blue. And it's in quotation marks because this is a rather intuitive wording of the Gauss-Markov theorem. Let's see what that really means. Blue means best linear unbiased estimators. All four parts. Best linear unbiased estimators. And the best linear part, best in this sense, means lowest variance of any linear estimator. And then unbiased means that the expected value of the estimator equals the parameter itself. And so what that means is that when we're doing ordinary least squares with these well-behaved data sets, it's like we're on a search for the truth of beta 1, and we're always closing in on it because although some estimates are high and some are low, the expected value of that estimator equals that parameter itself. So well-behaved data and errors is the key part of the Gauss-Markov theorem, and it means a lot. There are a lot of things that data and errors have to be in order to be considered well-behaved. First of all, that the true model is linear and is correctly specified by our regression equation that we've been using. Beta 0 plus beta 1 times xi plus epsilon I. There it is. That's what yi equals. And then the error term has a zero population mean. This means the expected value of those epsilon i's is equal to 0. So the error term is sometimes positive, sometimes negative, but it averages out to 0. Now, if the mean isn't 0, this is just kind of an aside. If the mean isn't 0, only the constant term is affected. But this is kind of an important aside. Look at the text on page 95 if you want to work through this example. And it says here, if we have our regular equation and the mean of the error term is 3, okay, where'd we pick 3? 3 doesn't have any significance here. It's just like, hey, pick a number. Okay, we'll pick 3. Then you can rewrite that as yi is equal to beta 0 plus 3 right there, and then epsilon I minus 3 over there. And since algebra tells us we can add and subtract the same constant from a side of an equation and leave that expression unchanged, we know that this is a true statement. Oh, but wait, look at this. That says that our constant term, as this equation is now rewritten, is a messed up form of beta 0 called beta 0 star, and then plus beta 1 times xi. And then our epsilon I is sort of a messed up version of our original error term. But hey, what's the error term of epsilon I star? Not epsilon I, the error term of epsilon I star. Well, in this, it's 3 minus 3, so the mean of that thing is 0. So what we have there is actually an equation that obeys that Gauss-Markov assumption. And that is why you'll hear this expression over and over, beta 0 is the garbage collector. Did you notice that beta 1 is unaffected? And that's usually the thing we're interested in. Like if we want to know how much tax collections go up when national income goes up, that's the marginal tax rate, and that's right there. Beta 0 is the constant term, or how much tax revenue we would get if income fell to 0. And we're usually not concerned about that, so having a messed up estimate of it doesn't matter. So that's why we call beta 0 the garbage collector. It collects the garbage of a non-zero mean on the error term and allows beta 1 to remain clean. And in the course of this class, we'll see some more reasons why beta 0 is messed up and therefore called the garbage collector. 3, all explanatory variables are uncorrelated with the error term. That means this rho thing, that correlation coefficient between x and the EI's there, that's equal to 0. Yeah, look at that. Now, the reason that we have to have this is that if x is highly correlated with epsilon, then when x goes up, hey, epsilon is coordinated with it, correlated. So x and epsilon are both high at the same time. So the observed y will be a really big number. But all ordinary least squares knows is that x went up and then y went up a whole lot. So OLS, ordinary least squares, will incorrectly attribute this to x. So that's why the rho, the correlation coefficient between the x's and the epsilons, has to be 0. Then, see how much you have to have in order for this to be well behaved? Then, the error terms have to be uncorrelated with each other. That is, they don't have autocorrelation or serial correlation. Now, when you write out the math here, and you can pause if you want to take this down, it says the population correlation between epsilon I and epsilon j is equal to 0 for every I that is not equal to j. And that's what that upside down A means, like for every. Yeah, there we go, just like that, for every. But this lack of correlation is actually the easiest to see diagrammatically and not so much with the equation. If you have no autocorrelation, and here we have these three possibilities, you can hit pause here and draw 3 diagrams. I recommend that. If we have, in each case, a y hat line, that's our estimated regression line, and we're going to see how this all looks. If you have no autocorrelation, then the dots are just randomly scattered around the line. They don't have a pattern. With positive autocorrelation, they look like, well, some people have called it a snake. See that snake twisting back and forth across the line there? That's positive autocorrelation. You have a string of positive errors followed by negative ones, like that. They run in strings. Negative autocorrelation is when you bounce back and forth across the line. If you have positive autocorrelation or negative autocorrelation, then the Gauss-Markov theorem does not directly apply. You have to have no autocorrelation to have a well-behaved data set. But that's not all. Fifth assumption, the error term has a constant variance. That is, it doesn't exhibit heteroskedasticity. Long word, pause the tape if you want to write it down. And once again, the math is a little less intuitive than the diagram. It says sigma I squared is equal to sigma j squared for every I and j there. And that's the variance of the error term. So we have 2 possibilities here. That those variances are homoskedastic or they're heteroskedastic. Greek word skedastic there meaning spread. So they have the same spread or they have different spread, heteroskedastic. And so what we have here is, once again, just to get the intuition, and it's always easier to draw the heteroskedastic one than the one that doesn't have any. Because the heteroskedastic one, typically you're going to see a pattern like this. The dots diverge from the line when it gets out like that. See, they're really close to the line over here and really far from the line like that. Well, when they are homoskedastic, they're about the same distance off the line wherever up and down the line you go. And they've got to be homoskedastic, no heteroskedasticity, for the Gauss-Markov theorem to directly apply. Then, no perfect collinearity. If you do have perfect collinearity, then it's meaningless. So what I'm saying here is you don't have any 2 variables that are perfectly correlated with each other. Because if you throw in 2 variables that are perfectly correlated with each other, then you can't run the estimation. Here is an example, predicting electricity demand with Fahrenheit and Celsius temperatures. We all know that electricity demand depends on the temperature. Hot summer temperatures cause the demand for air conditioning to go through the roof. So in your electricity demand estimating equation, you'd want to have the temperature there. But if you had the Fahrenheit temperature and you threw in the Celsius temperature, you'd be throwing in a perfectly correlated variable. And then you'd be violating this assumption, no perfect collinearity. And actually, the real reason that you couldn't get a good estimate is that deep down in your statistical package, it would be trying to divide by zero. It would be a divide by zero error. But just intuitively, if you've already got the Fahrenheit temperature, then the Celsius temperature doesn't add anything at all to your estimating equation because you've already got the information there in the Fahrenheit temperature. Now, there is an optional assumption. Wow, what do we mean? Optional assumption? That sounds weird, doesn't it? How can you have a theorem with an optional assumption? Well, here's what we mean by an optional assumption, that it's necessary for hypothesis testing, but not actually the Gauss-Markov system theorem here. So if you have all of those assumptions and you don't have this last assumption, your estimates are still best linear unbiased estimates. They're still blue. But if you want your hypothesis tests and your significance and all those things to run through, you need this additional assumption that the error term is normally distributed. And if it is, then you have good hypothesis testing of the kind that we've seen already. And that's a very important thing. And the central limit theorem is a help here because the central limit theorem tells us the conditions under which we can sample from a distribution that's not normal. Yeah, sample from a distribution that's not normal. And yet when we sample it and look at those samples, then those do turn out to be normal. Like you remember when we sampled from a binomial distribution and we got a normal distribution with those estimates. And here is just one thing to take with you. The error term is normally distributed in lots of financial markets. The error term is not normally distributed. Hey, how about that? Well, that's a topic for another day. But hey, you finance and QFin folks out there, the fact that that error term is not normally distributed is a source of your fortune. Hey, how about that? So that has been the hit and run on the Gauss-Markov theorem.